Hello, good evening, everyone, and welcome back to another session in this crash course for GATE 2021 exam preparation. I'm Vikas Sir, and I welcome you all to this session on power plant revision with important question discussion. So, good evening, everyone, and welcome to this session. I hope you guys are doing good. Hi, Raj Singh Jadon, very good evening. So, good evening, everyone, and welcome to this session on the power plant revision. Hi, Abhay Kumar, very good evening. Hi, Harshit, good evening. Very good evening to all my dear students. So today is 31st of December. I know that you guys, some of you must be thinking that we have to celebrate this New Year. Definitely, we all will celebrate New Year, but before that, we'll be completing this thermal. Thank you, Remo Ritvik, for giving so much respect to me. But I'm just a simple person who explain the concept of thermal and so make it easy for you to understand. Okay, but thank you so much for your good words. Hi, Kripesh Bethur, good evening. Hi, Sarat Lal, good evening. So very good evening, everyone, and welcome to the session. I hope you guys are doing good, and I hope you guys are excited to celebrate your new year with me. Yes, of course, because what could be best if we complete the entire revision of thermal that we have started, and we complete it today on 31st of December, that is the last day of the year 2020. Isn't it good that we guys will be partying together tonight, celebrating the success of completion of the subject of thermal and applied together on GATE Grade of YD channel, right? Hi Vikas Yadav, very good evening. Siddharaj Patil, very good evening. Welcome to the session. Hi Deepak Kumar Shah, very good evening. Harshit is saying, let's start a new year. Yeah, exactly. We will be starting the new year with the knowledge of the thermal, and we will be completing it with the knowledge of thermal. Okay, don't worry, thermal will be completed, but I will come back again in 2021 with more session on thermal, where we'll be revising the thermal with practice of questions, some more practice of questions. Okay, so trust me, I will make this subject so strong for you that in your GATE exam you will definitely be able to score good marks in this subject. That is definitely my resolution for 2021, that I will help you all to prepare for GATE 2021 in 2021. Hi Srinivas, very good evening. Hi Kripa. Yeah, tragedy year, yes, we can say 2020 have been full of lot of tragedies and lot of bad time, but definitely we are going to, this is about to end very soon and we will enter into 2021. So let's enter into 2021 with completion of the subject of thermal by completion of the power plant revision. Please give something in heat transfer. Well, Benny, actually heat transfer subject I don't teach. Basically, this is taken by Suraj sir. So he will be taking the subject of heat transfer. Suraj Gopi sir. Hi Srinivas, very good evening. Hi Vasu, good evening. Crystal Roy, good evening. Zubair, very good evening. So let's start the session with the revision. Guys, those who have joined me for the session also, please like the session, share the session also. Hi CC, very good evening. If that is your actual name, my dear. Oh, what I can see here is we have 33 students live and we have 20 likes. This likes and live are not exactly matching right now. Why? The number of live students are 33, but number of likes are just 20. Guys, please spend some time in liking the session also. Okay, so please quickly join me for the session. Well, thank you so much, Benny. Thank you so much. Hi, Sheenu. Very good evening. Okay. Yeah, definitely I will cover turbine and compressor also. So let's quickly start the session. Hurry up. Rupendra, very good evening. Let's start the session. Now we should not waste any time. So my dear students, I would like to start with my introduction first. I am Vikas Sir. I have 5+ year teaching experience. Did my MTech in thermal engineering from Thapar University, and I have mentored more than 10,000+ students for different exams like GATE, ESE and SCJE. My area of expertise includes subjects of fluid mechanics, thermal and applied and heat transfer subject. Okay, so let's start the revision. I will start with the topic of Rankine cycle first, and for some time I won't be able to take your comments when heat transfer review take place. Harshit, heat transfer subject I will not be taking. It will be taken by Suraj Gopi sir. So he will definitely take the revision of heat transfer. Don't worry. Now let's start this subject of power plant. We'll be starting with the Rankine cycle. As you know, it is a working cycle of steam power plant. It is a working cycle of steam power plant. So in the steam power plant, you know that steam is produced by burning of the coal in the boiler, in the furnace basically, and the heat of the furnace is given to working cycle of all the steam power plant. All the steam power plant which utilizes the heat, any kind of heat, whether it is the heat of the coal or the heat of the oil, in order to perform the combustion reaction, and the heat of that combustion reaction is basically provided in order to heat the water in the boiler. Okay, and then after getting heated up, it will change into steam. That steam will be supplied to the turbine for generation of for production of mechanical energy, and that mechanical energy will be further given to the generator for converting that into electrical energy. Okay, so basically in the ideal Rankine cycle we'll be having these four components: pump, boiler, turbine and condenser. These are the four major components of a Rankine cycle, ideal Rankine cycle. In that, what happens, basically the pump will be pumping the water, the feed water in the boiler. In the boiler, the heat will be supplied by combustion of the fuel. Generally in our country in India, for a steam power plant, we use coal as a fuel. In 67% of the power generation in the steam power plant is through coal. Okay, so coal will be basically, it will be undergo combustion with air in a furnace, and the heat of that coal will be provided to a boiler. In the boiler there will be some water which will be supplied by the pump. So feed water will be supplied by the pump, and that water will get heated up in the boiler. Okay, the boiler, when the water will get heated up, it will change into steam. But actually in the actual power plant, that steam is sent to the superheater. Okay, that will be sent to the superheater, and after that the superheated steam from the superheater will enter into the turbine. Okay, from the superheater. Now that superheated steam will be passed through a nozzle where the pressure energy or thermal energy of the steam will be converted into kinetic energy with the help of a nozzle. Okay, that is a part of the turbine. So now that nozzle will be providing high kinetic energy on the turbine blades. Because of that, the turbine blades will rotate. They will produce some mechanical energy. That mechanical energy will be transferred to the shaft of the turbine. Now the shaft of the turbine is connected to the shaft of the generator. This is connected to the shaft of the generator, which will be producing the electricity. Now the exhaust steam will be sent. The exhaust steam from the turbine will be sent to the condenser. In the condenser, heat rejection will take place by the cooling water. The cooling water will be supplied from a cooling tower. So cold water will be supplied and the hot water will go again to the cooling water. Okay, so condenser is a kind of a heat exchanger in which the heat rejection takes place and the steam will again change back into the condensate liquid. Or we can say the condensate liquid, which is actually the water coming out from condenser, will be again pumped back with the help of a pump into the boiler. So if you see the process in the Rankine cycle, we'll be using isentropic compression in the pump from 1 to 2. After that, there will be constant pressure heat addition in the boiler. Okay, then there will be isentropic expansion in the turbine, and then there will be constant pressure heat rejection in the condenser. Hi Akash Gautam, very good evening. Hi Vamsi, good evening everyone. Welcome to the session. Nikhil, yeah, definitely I will be taking some good questions in this here also in the power plant, because we were not having much time. That is why I was not able to take enough question for IC engine refrigeration, but I have taken 15 question. Today also I will take around 15 question, don't worry. So this is constant pressure heat addition in the boiler, this is constant pressure heat rejection in the condenser. Then it is isentropic compression in the pump, and then it is isentropic expansion in the turbine. So in the case of a Rankine cycle, sometimes you see that sometimes they will be starting the cycle from here. In some question, they will start the cycle from here. So you don't need to worry about it that whether the cycle is getting started from this particular point. Let us, this is point 1, this is point 2, this is point 3, this is point 4. Doesn't matter whether the cycle started from 1, this is given point 1, that is entry to turbine is given point 1 or entry to pump is given point 1. Doesn't matter. Ultimately, the efficiency will be equal to the net work divided by heat supplied. Net work will be turbine work minus pump work, okay, divided by heat supplied. Heat is supplied in the boiler, so it is simply, oh, my dear Senthil, if it had not been in the power plants in the GATE syllabus, Senthil Raj, then why I would be teaching here? I would have not wasted my energy in teaching the subject of power plant, my dear. Okay, so definitely it is in the syllabus of GATE 2021. Okay, for mechanical. So it is pump work is basically equal to, the turbine work is equal to, with respect to this diagram, the turbine work is H3 minus H4. With respect to this diagram, the pump work is equal to H2 minus H1. And the heat supplied will be equal to H3 minus H2. But with respect to this diagram, the efficiency will be equal to H1 minus H2 minus H4 minus H3 divided by H1 minus H4. So you have to be very much careful about this, that yes, Raju Chalani, the qualifier series will start from today. Okay, so you have to be very much careful that how the process have been started. The process has, this is the work of the pump can be found by change in enthalpy also, and work input to the pump can also be found as specific volume at entry to pump, at the entry to the pump, into the boiler pressure minus condenser pressure, and that should be in Pascal, that is should be in kilopascal. The two pressure should be in kilopascal, because generally they will give you the boiler pressure and condenser pressure in bar, so you have to convert to kilopascal as 1 bar. You can take it as 100 kilopascal. Okay, so this is also a formula for finding the pump work. Sometimes they will say that pump work is neglected. If it is neglected, then it is not a problem, but if it is not neglected, then you have to take the pump work. Okay, that is the important thing for finding the efficiency. Now there is a term called as work ratio. Work ratio is equal to the net work divided by turbine work, or it is equal to turbine work minus pump work divided by turbine work. This is the work ratio. Back work ratio is equal to the pump work divided by turbine work. The heat rate is equal to 1 by efficiency, or it is equal to heat supplied divided by net work. But one important thing is that the heat rate has got a unit. The efficiency has got no unit, but heat rate will be having the unit of kilojoule per kilowatt hour. This is a unit of heat rate. Okay, so remember this formula also, heat rate. One more thing, we have specific steam consumption. PDF will be available, don't worry. Hi Zafar Alam, good evening. PDF will be available in the Telegram group, don't worry. Specific steam consumption or steam rate. Okay, this is given by 3600 divided by net work output. Okay, specific steam consumption or steam rate basically tells you the amount of steam consumed in kilogram per hour to produce net work output in kilowatt. The unit here is kilogram per kilowatt hour. This is a unit of specific steam consumption. Clear? So these are some important formula from Rankine cycle that you have to remember. Now in the Rankine cycle, we are having a case of ideal reheat Rankine cycle. Okay, why do we do reheating? One more important thing is that before I tell you about this reheating, before that I have to tell you about two cases. That efficiency of the Rankine cycle also depends on the minimum temperature and the mean temperature. In terms of Carnot cycle, you can also write the efficiency of Rankine cycle in terms of minimum temperature and mean temperature. For example, if you have done the heat addition in the Rankine cycle, as you know that heat addition in the Rankine cycle is done at constant pressure. But if you want to compare the efficiency of the Rankine cycle in terms of, if you want to compare the efficiency of the Rankine cycle in terms of, because this has to be something here, okay, in terms of the Carnot cycle efficiency in terms of temperature, so we can assume a mean temperature at this point. We can assume a mean temperature such that, let us say this is the mean temperature line, and this mean temperature is the average temperature at which the whole heat addition takes place. It is a constant average temperature at which heat addition takes place. Heat rejection, as you know, it takes place at constant temperature already. The heat rejection takes place already at constant temperature, which is minimum temperature. So in terms of minimum temperature of heat rejection, in terms of mean temperature, this is the formula for efficiency. Now, if the mean temperature of heat addition will increase, the efficiency will increase. If minimum temperature will decrease, the efficiency will increase. Okay. Now, how to find this mean temperature? Let us say this is 0.1, this is 0.2, this is 3, this is 4. Okay. So, the mean temperature will be equal to S1 minus H1 minus H4 divided by S1 minus S4. This is how you can find the mean temperature of heat addition. Okay. I am telling you about reheating. Don't worry, Harshit. Okay. So this is a very important term about the mean temperature of heat addition. Also, the efficiency can be increased. Efficiency of Rankine cycle can be increased by decreasing the condenser pressure. By decreasing the condenser pressure. Efficiency can also be increased by increasing the boiler pressure. Increasing boiler pressure. And efficiency can also be increased by superheating. These are the three terms, but these are three parameters by which you can increase the efficiency. 7 p.m. started. Yes, 7 p.m. the class has started. This is the timing of the classes. Okay, the classes are going from the last 5 to 6 days. So that is the timing of the classes, 7 p.m. Okay, efficiency can be increased by decreasing condenser pressure, increasing boiler pressure, superheating, and by increasing the mean temperature of heat addition and decreasing the minimum temperature of heat rejection. This is how you can increase the efficiency of a Rankine cycle. Now there is another term called reheat. What is the purpose of reheating? Reheating in the Rankine cycle is only done to increase the dryness fraction. It is only used to increase the dryness fraction at exit of turbine. Reheating is only done to increase the dryness fraction at exit of turbine. That is the purpose of reheating. Why the reheating is allowed? Okay, you came today only. Okay, no problem. The poor kid, you can follow the classes. See, how is your new name, my dear? Please have a decent name, my dear, so that I can call you at least. Does it look good that I call you every time the poor kid? So it is my request to everyone that please have your original name or some decent name. It looks good for the faculty to call you, because I won't be able to call you every time in that case. Doesn't look nice. So in the reheat Rankine cycle, the main purpose of the reheat Rankine cycle is to increase the dryness fraction or the quality of the steam at exit of the turbine. Because generally it has been noticed that in the Rankine cycle, as you know that in the turbine the expansion of the steam takes place. But if expansion of steam takes place in the liquid plus vapor region, then it can cause the erosion of the blades of turbine. Okay, clear everyone? Is it clear to everyone? If suppose that I am having two cases, if I am doing the reheating, if we are having a normal Rankine cycle, there is one case if I am simply doing this. Sorry. And there is another case if I am just simply doing the reheating. If I am doing the reheating and then I am doing the expansion, then it will happen like this. So if you compare the dryness fraction in this particular case, the dryness fraction at 0.2 is greater than 0.1. So basically, in the case of if you don't do the reheating, then what will happen? If you don't do the reheating, then what happens? The quality of the steam is decreased. and because of that the blade of the turbine can get corroded. So what is the purpose of reheating? The reheating is basically done to increase the dryness fraction by reheating. So in that we basically will between two turbine, one high pressure turbine and one low pressure turbine, will be using a reheater. Okay, a reheater will be used. This is a reheater. A reheater will be used between a high pressure turbine and a low pressure turbine. Okay, now try to understand it very carefully. Now this is a question that comes in your mind. What happens with reheating? With reheating, the turbine work will increase. The pump work is not affected. Pump work is same, it is not affected. The net work will increase. But with reheating, heat supplied also increases. But now the question is, okay, now you have changed the name. That is so nice of you, Shri Krishna Mishra. You have such a nice name, decent name. Now it looks nice, right? So the turbine work has increased. The heat supplied has also increased. Okay. Now, my dear student, try to understand it very carefully. With reheating, only in Rankine cycle, the efficiency will increase. Efficiency will increase if we use only single reheater. If we use a single reheater, then efficiency will increase with reheating in Rankine cycle. But or simply say that we say that if the optimum reheat pressure is equal to 0.2 to 0.25 of the boiler pressure, if the optimum reheat pressure is 0.2 to 0.25 of boiler pressure, yes, Shaktiman, definitely I will take the revision marathon session of all the subjects, don't worry, okay? So my dear students, the reheat pressure is equal to 0.2 to 0.25. This is the optimum reheat pressure, and under this condition, the efficiency will increase. If the reheat pressure is equal to 0.2 to 0.25 of the boiler pressure, then efficiency will increase with reheating. But if the reheat pressure becomes more than that, then efficiency will decrease. Okay. In exam, in the exam they ask you that what happens with reheating. So with reheating, you have to remember that when you do reheating, the efficiency will increase. Okay, with the efficiency will increase with reheating only up to certain pressure, up to single reheater. If you use a single reheater, but at least if that question comes in exam, you have to mark that this is correct. Yes, efficiency will increase with reheating. Okay, only in the case of Rankine cycle, not in Brayton cycle. What is next is regeneration. Regeneration is basically regeneration. What is the purpose of the regeneration? Regeneration is basically a only method by which the efficiency will increase. If we have to increase the efficiency by reducing the heat supply, then the method that is used is called regeneration. Okay, so what is the purpose of regeneration? In the regeneration, we will take some steam, that is bleed. We will bled some steam. During expansion in turbine. We'll bled some steam during expansion in turbine, and we will give this steam to a feed water heater. Now these feed water heater are of two types. One is feed water heater are of two types. One is open feed water heater, another is closed feed water heater. Open feed water heater are basically called as deaerator. Open feed water heater or deaerator, and closed feed water heater. Closed feed water heater is a feed water heater which is like a shell and tube heat exchanger. So closed feed water heater is like a shell and tube heat exchanger. Okay. Now what is the difference between the open and closed type? Open type there will be direct mixing. Direct mixing of steam and water. And here there will be indirect mixing of the steam and water in the closed type. So closed type will be like a shell and tube heat exchanger where there will not be direct mixing But in the deaerator, which is open type feed water, deaerator is basically what? The steam will come from open feed water heater. The steam will come from this side. The feed water will come from this side. Okay. So why it is called as deaerator? Because it is used to remove the non-condensable gases, to remove non-condensable gases. Okay, it is used to remove the non-condensable gases from the feed water, because the feed water contains some those gases which are not which do not get condensed in the condenser. So those non-condensable gases will be released with the help of a vent, in the open feed water heater. Those non-condensable gases will remove from here. Okay, that is the purpose of open feed water heater as a deaerator. So in a steam power plant, we use at least one deaerator or one open feed water heater. Okay, that is the minimum requirement. There should be at least one open feed water heater. Okay, see, my dear students, it is my humble request to all of you. I will answer all your questions, whether I will be taking any class or not, what will be my schedule for the next 1 month. All the question will be answered. But right now we have more important priority, that is to cover the revision and solve the questions of power plant. So let us do that first. After that, if you are having any general question or query, I will definitely happy to answer that. Okay. So open feed water heater or deaerator is basically a type of a feed water heater in which the steam will be taken from the turbine during the expansion. Important thing is that during expansion, bleeding is the formula. Bleeding basically means that in regeneration we use the term bleeding. Bleeding means we are taking the steam during the expansion in turbine, and we'll be giving this steam, we'll be providing that steam to the open feed water heater. So let us say that 1 kg of steam is sent from the boiler to the turbine. Let us say y kg steam has been taken by that open feed water heater. Okay, and the leftover steam, that is 1 minus y kg steam, will be sent to the condenser. It will be released, it will be given to the condenser. So basically y kg comes here, 1 minus y will go to the condenser. Again this will 1 minus y will come here, then again 1 minus y will come here. After that these two get mixed. Here you will be again getting 1 kg again back. Okay, so we have to remember the, sorry, I need a blank page. Let me just get a blank page. Yes, what is your question? Covered in power plant. See, if you are having any query, my dear, you can ask me, but let me just let me just teach you, because right now we have got time for teaching. Okay, class ki timing is at 7 p.m. Okay. So my dear students, if you see the energy balance equation, let us say this is your feed water heater, open feed water heater. Energy balance is very important. The energy balance in open feed water heater. This is very, very important. Now, what is the energy balance in open feed water heater? Let us say that y kg steam has been taken. Y kg steam has been taken at what condition? At 0.2. At 0.2 y kg steam has been taken for feed water heating, and left over 1 minus y kg will be sent to the condenser. Again 1 minus y kg will come here. Again 1 minus y kg will come here. So 1 minus y kg and 1 minus y kg. 1 minus y kg steam will be sent at 0.5, having enthalpy H5. This will be having enthalpy of 2. And here you will be getting 6. At 0.6 you will be getting 1 kg of steam after mixing. So by law of conservation of mass, y kg steam will mix with 1 minus y kg to give you 1 kg back. Okay, but if you apply the energy conservation, by conservation of energy, we'll simply say that y into H2 plus 1 minus y into H5 will be equal to S6. Okay, so from here you can simply say that YH2 plus H5 minus YH5 is equal to S6. So from here you can simply say that your Y will be equal to S6 minus S5 divided by H2 minus H5. So in this way you can find the amount of steam taken for heating in the feed water. This will give you Y is the, what is Y? Y is the steam bled from turbine. Steam bled from turbine. So what is the advantage of this steam bled from turbine? What is the advantage of getting this thing? The main advantage of getting this thing is that now in the reheating, the turbine work will become H1 minus H2 plus 1 minus Y times of H2 minus H3. This will become turbine work. The pump work will become 1 minus Y times of pump work is between 5 to 4. So this is H5 minus H4 plus S7 minus S6. And the heat supplied will become H1 minus S7. This will be the only heat supplied. So you can see the heat supplied has reduced. It has become H1 minus S7. So the main advantage of the regeneration is the heat supply has reduced. Okay. So that is the main advantage of regeneration. So with regeneration, heat supply has reduced, efficiency will increase. You have to remember that. Okay. This is how you can find the efficiency. You can find the turbine work, you can find the pump work, you can find the heat supply. Just put everything here in this formula. Efficiency will be equal to turbine work minus pump work divided by heat supplied. You'll be getting the efficiency of the regeneration cycle. Clear everyone? This is the Rankine cycle. So we have completed the revision of Rankine cycle in 22 minutes or 24 minutes. Let's move on to the Brayton cycle quickly. So Brayton cycle is the working cycle of the gas turbine power plant. Please again explain reading. So my dear, I Shubham Pandey, this is not a theory class, my dear, and you know the timings. So please, I'm very sorry. Basically you can, you know the timing of the classes, and you are the one who comes daily in the class. If someone who does not come daily in the class, that is another thing. But those students who come daily in the class and you know the timings, so you should come on time, because I am not going to repeat anything, because I don't have much time of repeating the things. Because it is not the only thing that I have to teach today. I don't have to teach Rankine cycle. I have to teach everything. Okay, it is a revision session. So if you have not understood bleeding, you can again see the session. I have explained what is bleeding. Okay, really sorry about this. I cannot give you time for that. Closed feed water heater. See, it is open feed water heater or closed feed water. They will be having same effect. Only difference is that in open feed water heater is a deaerator. Okay, and in deaerator, the non-condensable gases from the feed water are removed. That is why we use an open feed water heater, and one open feed water heater is compulsory, and 3 to 4 closed feed water heater are used in the power plant. Okay. Now let us study about the Brayton cycle. Brayton cycle you can call it as Brayton or Joule cycle. It is a working cycle of gas turbine power plant. Working cycle of closed gas turbine power plant or closed gas turbine cycle. The working cycle of closed gas turbine power plant is the Brayton cycle or Joule cycle. Hi Arvind, very good evening. Welcome to the session. So in the Brayton cycle, we'll be having these components: compressor, heat exchanger, turbine, and heat exchanger. This heat exchanger is a combustion chamber. Basically, it is a combustion chamber in which heat is added at constant pressure. Okay, so heat is added at constant pressure here, and this is a heat exchanger where heat is rejected at constant pressure. Compression, and the working fluid here will be gas. The working fluid will be gas or ideal gas in the Brayton cycle. Clear? So my dear students, the gas or ideal gas will enter in the compressor from the heat exchanger after heat rejection. This will get compressed in the compressor. The pressure and temperature will increase. Then that hot gas will be, after compression, it will be sent to the heat exchanger, which is a combustion chamber. Efficiency increment is only possible by regeneration. That is correct. Okay. So in the combustion chamber, what will happen? The heat addition will take place along with the air. Some fuel will be mixed with air and combustion will take place. And the hot gases after release after combustion will be sent to the turbine. The turbine will produce the work. Some of the work will be used for driving the compressor. and then it will be rest of the work will be used for producing electricity. The hot gases released from the turbine or exhaust gases released from the turbine will be sent to a heat exchanger, and their heat rejection will take place, and after cooling the gases will again be sent to the compressor. Okay, so in the Brayton cycle we have 1 to 2 isentropic compression, then constant pressure heat addition, then again isentropic expansion, and then constant pressure heat rejection. So if you have to draw this cycle on the temperature entropy diagram, so this is a isentropic process, and this is constant pressure, and this is again an isentropic process, this is constant pressure. Okay, so this is how you draw all the process on the Brayton cycle. Okay, temperature entropy diagram. This is 1 to 2, 3, 4. Clear everyone? So this is the Brayton cycle on the temperature entropy diagram. Clear everyone? Yes, is it clear to everyone? Please tell me. Hi Nitin Krishna, very good evening. Good evening everyone, and welcome to the session. So now in the Brayton cycle there are some important points that I have to tell you. In Brayton cycle the important point is if compression and expansion are isentropic. If compression and expansion are isentropic in Brayton cycle, then you have to understand the formula of efficiency. Then efficiency of the Brayton cycle will be equal to 1 minus 1 by pressure ratio of gamma minus 1 by gamma. Okay, clear everyone? Yes, this is the formula for efficiency of the Brayton cycle if the compression expansion is isentropic. Clear? Now very important point you have to listen here, very important. If compression expansion are not isentropic, then what will happen? In that case you cannot apply this formula. In that case, how can you solve this question? I need a blank page again. See, I am getting short of blank page, so I have to use a blank page now. What if you don't know the value of, if compression expansion is not isentropic, if mechanical efficiency are given, then what will happen? In the actual Brayton cycle, they also give the mechanical efficiency. Let us say this is 1, this is 2, isentropic. But if this is actual, let us say this is actual compression. This is 3 to 4s, isentropic, this is actual compression. Okay, so if the mechanical efficiency of compression is given and turbine is given, then what you have to do, you know that that mechanical efficiency of compression is equal to the isentropic work of compression, isentropic work divided by actual work of compression. If this is the actual Brayton cycle. In actual Brayton cycle, the compression expansion are not isentropic. Okay, this is very important. Very good. You guys are giving right answer. Very good, absolutely correct. I'm very happy to see that. Isentropic work will be H2S minus H1 divided by H2 minus H1. Because it is an ideal gas, enthalpy is a function of temperature also. So you can also write it as T2S minus T1 divided by T2 minus T1. So if we have to find the efficiency, you can use this formula. And from this formula, you can find the value of T2 from here. Similarly, you can find the isentropic efficiency of turbine. This is equal to actual work divided by isentropic work. Okay. So you will get the value of actual work will be HT minus H4. Isentropic will be HT minus H4S. Okay. So you can say T3 minus T4 divided by T3 minus T4S. So how to solve the question in that case? Firstly, if you have to find efficiency, you have to find the value of T2S. T2S by T1 is equal to pressure ratio over gamma minus 1 by gamma. From here you will get T2S. But T2S is not required for the efficiency. Because efficiency of the Brayton cycle will be equal to what? Turbine work minus compressor work divided by heat supplied. If compression expansion are not isentropic. If compression and expansion not isentropic. In that condition, this is the efficiency formula. In that case, you have to find the actual work of turbine. My dear. So this will be H3 minus H4 minus H2 minus H1 divided by H1 H3 minus H2. That means you have to find this value and this value of enthalpy. Or you can also apply in terms of temperature. This will be T3 minus T4 minus T2 minus T1 divided by T3 minus T2. That means T1 and T3 will be given. T1 and T3 will be given in the question. That is minimum temperature and maximum temperature of Brayton cycle will be given. You have to find these temperature T2 and also T4. You have to find T4 and T2 from this equation of isentropic efficiency of turbine and compressor. And by putting this in this formula, you will be getting the efficiency. Is it clear to everyone? If compression and expansion are not isentropic, then this approach will be followed for solving the question of efficiency. Clear everyone? Clear? Please tell me, clear or not? Yes. Is it clear to everyone? Please tell me. It is very, very important thing, because many a times when question comes in your GATE exam, they will give you the mechanical efficiency in compression or turbine, and they can ask you to find the efficiency. So if the mechanical efficiency is given for compression and turbine, then you have to find this temperature, actual temperature at exit of compression turbine, and then you have to put in this formula to find the efficiency. T1 is the minimum temperature given. T1 is the minimum temperature of Brayton cycle. T3 is the maximum temperature of Brayton cycle. That will be given in the exam. Okay, you have to find T2 and T4. T2 and T4 from here. Clear everyone? Now there are some more important formula that you have to remember. Back work ratio. Back work ratio in a Brayton cycle will be also equal to negative work by positive work. That means compressor work by turbine work. Work ratio is equal to net work by positive work, that is turbine work minus compressor work by turbine work, or work ratio is equal to 1 minus back work ratio. One more important formula I have to tell you. Practical example, don't worry, I will be solving the question also in this class. We are talking about the practical example, we will be solving the questions. Do you want me to give the practical example of this thing? The simple practical example, Harshit, is, you know that isentropic process is an ideal process. It is not a real process. Okay. In the real application, there will be some friction. There is no possibility that in a mechanical component like compression and turbine, there is no friction there. There will be some friction. And because of the friction, the compression and expansion are never isentropic in the practical situation. Okay, so in the practical situation, you have to take the compressor and turbine mechanical efficiency. Okay, now I have to tell you that work ratio which was equal to turbine work minus compressor work divided by turbine work. You know that turbine work will be equal to T3 minus T4 and compressor work will be T2 minus T1 divided by T3 minus T4. If you want, you can write it in this form, T2 minus T1 divided by T3 minus T4. If you do some rearrangement, I am telling you the shortcut only, my dear. If you do some rearrangement, then what you will be getting here? 1 minus, this will be getting 1 minus T1 of T2 by T1 minus 1 divided by 1 minus T4, T3 by T4 minus 1. This will get cancelled out because you know that for Brayton cycle T2 by T1 is equal to T3 by T4 is equal to pressure ratio of gamma minus 1 by gamma. So we can say that work ratio is equal to 1 minus T1 by T4. Sometimes they can ask you to find the work ratio. They will give you the temperature at the inlet of compressor. See, my dear student, please, I am telling you, please guys focus on the lecture, okay? Because I have to cover a lot of things. Do not, if you are having some doubt, good, you can ask that. But let me just complete the revision because it is very, very important. So my humble request is, let me just tell you, I will not leave anything. I will cover everything, okay? Work ratio is equal to this 1 minus T1 by T4. If T1 is given minimum temperature and the turbine exit temperature, you can use this formula for work ratio. Work ratio can also be found by using this formula. It is also equal to 1 minus T1 by T3. That is minimum temperature by maximum temperature. Pressure ratio of gamma minus 1 by gamma. This is also the formula of work ratio. See, I can do the derivation because here I don't have to tell you the derivation. We don't have much time, but otherwise we can derive that also. If you take common T1 by T3 here, if you take T1 and T3 outside, ultimately from here you will be getting this relation. But I am not here deriving the relation because you have to remember this formula for work ratio. So if you know the work ratio, you can easily find the back work ratio. Okay, clear? Clear everyone? Yes, my dear student. Is it clear? Okay. So that is the formula for back ratio and back work ratio. If the exam question comes, then you have to remember this formula for work ratio. Okay, it can be written as 1 minus T1 by T4, or it can be written as 1 minus T1 by T3, or it is equal to 1 minus minimum temperature by maximum temperature pressure ratio over gamma minus 1 by gamma. This is the formula for work ratio. Clear everyone? Let's see the another temperature. Now there are condition of I will tell you about this thing, don't worry. I will tell you about this thing. Now next is air rate. Air rate is equal to mass of air divided by net work. Air rate is very similar to steam rate. Like we have studied the steam rate in the case of Rankine cycle, here we will be studying about the air rate. So air rate is equal to mass of air required in kilogram per hour divided by net work output in kilowatt. So air rate is equal to 3600 divided by net work, that is kilogram per kilowatt hour. Okay, clear everyone? Air rate is the criteria of size of plant. Lower the air rate, smaller will be the plant size. Matlab, air rate tells you how much amount of air is required in kilogram per hour to produce net kilowatt of work output. That is the meaning of air rate. Okay. So air rate basically tells you more is the air rate, more will be the size of the plant. Less is the air rate, less will be the size of the plant. Okay. Specific power is equal to net work divided by 3600. That is called specific power. So these are some important formula that you have to remember. Now this is a very important condition of optimum pressure ratio. Basically what happens in the case of Brayton cycle, as you know that efficiency is equal to 1 minus 1 by pressure ratio of gamma minus 1 by gamma. You all know this formula. So you can totally relate from here this formula that if pressure ratio will increase, the efficiency of Brayton cycle will increase. But important thing is how much should be the increase in pressure ratio? How much maximum you can increase the pressure ratio? Okay. Now, as we know that in Brayton cycle, minimum temperature is fixed. Minimum temperature is that temperature at which the air enters into the compressor. That is fixed temperature, because generally the air enters the temperature at atmospheric condition. And also the maximum temperature of the Brayton cycle is fixed. Why? Because of the metallurgical condition of the blades of turbine. So maximum temperature in the Brayton cycle is limited to 1300 Kelvin. You cannot cross maximum temperature of 1300 Kelvin in Brayton cycle because of metallurgical condition of the blades. Blades cannot hold maximum more temperature more than 1300 Kelvin. So these two temperatures remains fixed in the Brayton cycle. So how much you can increase the pressure ratio? Maximum increasing the pressure ratio you can go up to by doing the compression. Maximum you can go up to when T2 will become equal to T3 or T maximum. This is the maximum amount of compression you can do when the temperature after compression becomes equal to the maximum temperature of the cycle. This is the maximum temperature compression you can do, and in that situation the maximum pressure ratio will become the T maximum over T minimum divided by gamma over gamma minus 1. This will be the maximum pressure ratio of the Brayton cycle. In that situation, the efficiency will be equal to 1 minus T minimum by T maximum. In that situation, efficiency will become equal to Carnot cycle efficiency. But the problem here is that with maximum pressure ratio, the net work output will be 0. Why? Because when you do the maximum pressure ratio, when you increase the pressure ratio to maximum, the compressor work becomes equal to turbine work. The compressor work will become equal to turbine work, and so net work will become 0. So under maximum pressure ratio condition, the net work is 0. That is why we have to find the optimum pressure ratio. Optimum pressure ratio is that pressure ratio at which net work becomes maximum. And that optimum pressure ratio is given by, my dear, again I need a blank slide. See, I don't know how much content I have to add. So let me just add the blank slide. Okay. Okay. Now what is about the optimum pressure ratio? Optimum pressure ratio is that pressure. There is a derivation for optimum pressure ratio also, but I don't have to teach you derivation here because we don't have time for that. Optimum pressure ratio of Brayton cycle is equal to maximum temperature divided by minimum temperature over gamma over 2 times gamma minus 1. This is the formula for optimum pressure ratio, and under this optimum pressure ratio, the maximum work output will be equal to Cp of root of T maximum minus root of T minimum whole square. This is the net maximum work you will be getting from the Brayton cycle under optimum pressure ratio, and the efficiency, optimum efficiency, will be equal to 1 minus root of T minimum by T maximum. This will be the optimum efficiency of the Brayton cycle. Okay, these are the very important formula: the optimum pressure ratio, the max net work output, and for the condition for net work output is that the T2 will become equal to T4 will become equal to root of T1 T3. This is a condition for maximum pressure ratio, or condition for maximum work output in Brayton cycle. Okay, clear everyone? These are some important formula that you have to remember. One more important thing, sometimes for finding the optimum pressure ratio, they will also give you the compressor and turbine efficiency. If these are given, then how can you find the optimum pressure ratio? Then in that condition, your optimum pressure ratio will be equal to, the compressor efficiency into turbine efficiency into T maximum by T minimum. That will be multiplied power gamma over 2 gamma minus 1. This will become the formula. If the compressor and turbine efficiency, isentropic efficiency is given, then the optimum pressure ratio will be given by this formula. Clear everyone? Yes, is it clear to everyone? These are some important formula that will be required for solving the questions for Brayton cycle. Yes, clear? Tell me everyone, is it clear to everyone or not? Hurry up, quickly tell me. These are very important formula for Brayton cycle. Okay. Now next is there are three conditions of Brayton cycle. One is Brayton cycle with reheating, intercooling, and regeneration. Brayton cycle with reheating has nothing to do with the efficiency. Reheating in the Brayton cycle is only used to increase the turbine work and the net work. With Brayton cycle with reheating, turbine work will increase, net work will increase, but the efficiency will decrease. प्रेशर के टर्म्स में भाई, प्रेशर के टर्म्स में बता चुका हूं फॉर्मूला. आई हैव ऑलरेडी टोल्ड द फॉर्मूला. ओके, डोंट वरी, आई हैव टोल्ड यू एवरीथिंग. विवेक अग्निहोत्री. ओके, whatever is required for your gate exam. Okay, so Brayton cycle with reheating. Why we do reheating? Reheating is only done to increase the turbine work in the Brayton cycle and the net work. And with reheating, the efficiency will always decrease with Brayton cycle. Always remember that. So in the Brayton cycle with reheating, what we do, we'll be using two turbines. One is a high pressure turbine, another is a low pressure turbine, and between those two turbines we'll be using a reheater. So what is the effect on? Yes, Lalit Raj, optimum pressure ratio decide the network output. Okay, there's a derivation for that. The network output will become maximum when the T2 and T4, that is the temperature and exit of compression turbine, will become geometric mean of the minimum and maximum temperature. That is a condition, and from that condition we getting the maximum work output. Okay, see, some of the students are have not come here for revision. Some of you have come for actually understanding the subject. See, my dear, I have no problem in that, but right now this is not the platform for that. This is not the right event for that, because in this time I'm not basically taking a revision of each particular subtopic. I'm taking the revision of each subject. So try to understand, we don't have much time for clearing each single important things, right? I cannot go on each and every topics. We are simply revising the whole subject. So basically in the reheating, what we do, will be using a high pressure turbine, will be using a low pressure turbine, and in that will be between you will be using a reheating. So what will happen with reheating? The heat supply will increase, the heat rejected will increase, the turbine work will increase, net work increase, efficiency will decrease. That is the effect of reheating. So with reheating, what happens? No change in compressor work. Compressor work is not affected. Turbine work increase, net work increase, both heat supplied and heat rejected increase, efficiency will decrease. This is the effect of reheating. Okay, so reheating only is used for increasing the turbine work, but efficiency will decrease with reheating. With intercooling in the Brayton cycle is only done to reduce the compressor work, increase the net work. The heat supplied will increase, the heat rejected will increase, the efficiency will decrease. So in intercooling, what we do, will be using two compressor, and between two compressor we'll be using an intercooler. Intercooler is like a heat exchanger which will reject the heat. That is an intercooler. It will reject the heat at constant pressure. Okay, so this is the first compressor, this is the second compressor. Between these two compressors, sorry, this is the second compressor, and between this compressor we'll be using an intercooler. This is the intercooler. Okay, so basically intercooling is in the Brayton cycle is used to reduce the compressor work, increase the net work. But what is the effect of that? The effect is that efficiency will decrease. Okay, so that is the effect of intercooling. Decrease in compressor work, no change in turbine work, net work will increase. Both heat supplied and heat rejected increase, efficiency will decrease. Okay, so I have to tell you a very important point here. In the case of a Brayton cycle, only reheating, what will happen? Turbine work will increase, compressor work will be same, net work will increase, but efficiency will decrease. Only intercooling, compressor will decrease, turbine work will be same, net work increase, efficiency decrease. So my dear, it is very clear from this that if you only do reheating and intercooling in Brayton cycle, then they might increase the net work, but they will not increase the efficiency. So that is why we have to combine reheating and intercooling with regeneration. That is why regeneration is needed. Okay, so what is regeneration in Brayton cycle? In Brayton cycle, regeneration simply means that it is very similar to Rankine cycle. Only difference is that in Rankine cycle for regeneration, we were taking some steam during the expansion in turbine. During expansion turbine, we were taking some steam and we were giving that steam to a feed water heater. In case of Brayton cycle, the gas will be used for regeneration, but that will be exhaust gas after expansion in the turbine. That exhaust gas after expansion turbine will be given for regenerator, will be given to the regenerator. Now regenerator in the case of a Brayton cycle will be a counter flow heat exchanger. It is like a counter flow heat exchanger, in which, what is the counter flow heat exchanger? The hot fluid will come from this side, and the cold fluid which has to get heated up, it will come from this side. What is the cold fluid? It is the compressed air. The compressed air from the compressor, which generally goes into the combustion chamber, right? But suppose for regeneration, what we have to do? In regeneration, the heat supply will decrease and efficiency will increase, and net work output will be same. Net work output will be same. No effect on net work output in the case of regeneration in Brayton cycle. Net work output will not be affected anyhow. Okay, net work output will be same. Clear everyone? नहीं भाई, खूब डिसलाइक मारो डिसलाइक करो डिसलाइक, बहुत मजा आ रहा है ना डिसलाइक करने में. नहीं, some people have got this only one intention. They come in the class to test the knowledge of the faculty, to get something like asking their question, and when they don't get anything, they will come and go and dislike the session. My dear, this session is not here. Try to understand the importance of the session. They are very, very important. छाया यादव सिंह, इसमें 44 से ज्यादा कोई लाइव नहीं है होता. सिस्टम नहीं सही है, सिर्फ हवा बना रखा है गेटअप वालों ने. Okay, good. Thanks everyone for the positive comments. So my dear students, in the Brayton cycle with regeneration, you have to understand very important thing, that the compressor when it is coming from the compressor coming from the compressor, which has to go into the combustion chamber, right? It will not go into the combustion chamber directly. It will first pass through a regenerator. In the regenerator, it will take the heat of the exhaust gases. The exhaust gases which are sent from a turbine, those exhaust gases will give their heat to the compressed air. The compressed air will get heated up. The compressed air will get heated up, and after heating, now it will get more heat. It will get more, and because of that, my dear students, we have to supply less heat in the combustion chamber. In combustion chamber, we have to supply. Is I hope there is no buffering issue. Is there any kind of buffering issue? Yes, I hope everything is fine. I think there is no buffering issue. Is it fine? Clear? चलिए फिर let's continue. Let's continue. Okay, fine, fine. Now fine, okay, fine. Yes. So my dear students, the main purpose of the regenerator here is to in the regeneration, the exhaust gases will give their heat to the compressed air. The compressed air will take that heat. It will become more heated. Now, because your compressed air has got more heat, then less heat will be supplied in the combustion chamber. Okay, so ultimately the heat supply will reduce. So in the case of a Brayton cycle with regeneration, what happens? This is, let us say, 1 to 2 compression. Then after that, generally the heat addition is from 2 to 3, but this is 3 point. This point is 0.5, let us say. This is 0.4, and let us say this is 0.6. Clear everyone? So this is the point of exhaust gases are these. These are the exhaust gases. This is the regeneration heating, the heating in regenerator. Heat supplied in the regenerator. So this is the actual heat supplied in the combustion chamber. So my dear, what is the effect of regeneration? The heat supplied in regenerator in the combustion chamber has reduced. So because of that, what happens? Okay, so because of that, the actual heat supplied in the combustion chamber is now equal to H3 minus H5. Earlier it used to be H3 minus H2. Now this much amount of heat is not required to be supplied in combustion chamber because this much heat the gas has taken from the regenerator. This is the amount of heat added by regenerator. So gas have already become hot. They have reached to this point, 0.5. Now they will be sent to combustion chamber at 0.5. So this much amount of heat will be added in combustion chamber. So heat supply has actually reduced. What will happen to turbine work? See, turbine work is same. Turbine work is same. Pump compressor work is same. Net work is same. Okay. There is one more important formula in the case of a regeneration, that is effectiveness of the regenerator. This is the effectiveness. As you know that the regenerator in the case of a Brayton cycle is a counterflow heat exchanger, and the counterflow heat exchanger this effectiveness is equal to actual heat divided by maximum heat. Okay, so what is the amount of actual heat? Tell me. The actual heat in the regenerator is equal to H5 minus H2. This is actual heat in the regenerator. Divided by maximum possible heat will be equal to what? Difference of the temperature of the hot fluid. This is the temperature of the hot fluid, and this is the inlet temperature of the cold fluid. That is T4 minus T2. This is the formula for effectiveness. Sorry, this is H4 minus H2. Or is it fine now? Is it fine? Is it fine now? Please tell me. Is it fine? Please tell me everyone quickly. Fine? Oh, really sorry about this. I don't know what is happening to my internet. Generally, it does not happens, but can't see me. Is it fine now? Please tell me. Is it fine? Yeah, there was some. There is some. Actually, as you know, that internet. There is some fluctuation in the internet. I have just seen my internet connection. It is having some blinking in the that Wi-Fi connection is having some blinking right now. So that is why it is causing the problem. Okay, clear everyone? Okay, yeah. So no problem. Is it fine now? Can we continue? I think it is fine now. Yeah. So let's continue now. Okay, fine. So let's continue now. I was telling you about the effectiveness. So basically what I was telling you that effectiveness of any heat exchanger is equal to actual heat transfer divided by maximum heat transfer. What is the actual heat transfer in the regenerator? Actual heat transfer in the regenerator is this much. This is the actual heat transfer. What is the maximum possible heat transfer? If you have studied the topic of effectiveness, heat exchanger, in heat exchanger there is a term called effectiveness. Effectiveness in the heat exchanger is equal to temperature of the hot fluid. For example, temperature of the hot fluid, cold fluid exit minus temperature of cold fluid inlet divided by temperature of the hot fluid inlet minus temperature of the cold fluid inlet. This is the formula of the effectiveness of the heat exchanger. You know this formula, right? Here the cold fluid is compressed air. This is the exit temperature of the cold fluid. This is TCE. This is the inlet temperature of the cold fluid. This is TCI, T1. This is the inlet temperature of the hot fluid, THI, T4. So basically the effectiveness will be equal to what? H5 minus H2. H5 minus H2, which is the actual heat transfer in the regenerator, divided by H4 minus H2. This is the maximum possible heat transfer. What is the maximum possible heat transfer? Difference of the maximum temperature of the hot fluid minus the minimum temperature of the cold fluid, right? Here the maximum temperature is T4 of the hot fluid and minimum temperature of cold fluid is T2. Cold fluid is that fluid which is coming from the compressor, which is getting heated in the regenerator. Okay, so this is the formula for effectiveness of the regenerator, and this is the formula for efficiency of an ideal regenerative cycle. What is the effect of regeneration? Okay, the effect of the regeneration is no change in compression turbine work, net work remains same, both heat supplied and heat rejected decrease, mean temperature of heat rejection increase, mean temperature of heat rejection decrease, cycle efficiency will increase. Okay, so always remember this is very important, that with intercooling and regeneration, if you combine the intercooling and regeneration, then what will happen? The compression work will decrease, net work will increase, turbine work will be same, the efficiency will increase with the, because heat supply will reduce. With the reheating and regeneration, what will happen? With reheating and regeneration, the turbine work will increase, the net work will increase, the compressor work remains same, the efficiency will increase. So if we combine the regeneration with intercooling and reheating, then you will see that both turbine net work and efficiency are increasing. Okay, so always remember that we always combine the net intercooling. Intercooling is always combined with the regeneration, and reheating has also to be should be done with regeneration. Okay, clear everyone? Hi, good evening everyone. Okay, some students are leaving the session. I don't know why. What is the reason behind that? See, internet issues are not being caused by me. As you can understand, you guys are engineers and you totally understand this thing. You guys are technical persons. Okay, so if you guys think that internet issues is caused by the faculty or the someone who is teaching, this is not possible. Actually, it is a loss to me also, because my 5 minutes have got wasted because of the internet issues. Okay. Now we are going to understand the compressor. Different types of compressors are there. Compressor basically the device which is used to increase the pressure and temperature of the gas. It is used for gas, air or vapor. Okay, so basically compressor is a device which is used to increase the pressure temperature of a compressible fluid. Compressible fluid. Now these compressible fluid, the compressor are of different types. It can be positive displacement compressor. Positive displacement compression simply means that in these compressor, some gas will be basically placed inside either a reciprocating engine or inside a rotary engine, something like that, or it will be a reciprocating device or two-flow motion device like a cylinder, or it can be a rotating device. In that the air will get compressed. Okay, clear everyone? In the case of a positive displacement device, basically what we do, we reduce the volume. We reduce the volume in a small space and we increase the pressure. By reducing the volume or by having a displacement of the gas and by causing reduction of the volume, we will increase the pressure. So this will happen in the positive displacement. Why it is called positive displacement? Because you are displacing the gas, you are displacing the air, and by displacement of the air you are getting something positive. You are getting increased pressure or high pressure. So in positive displacement compression, we'll be studying the reciprocating compression, rotary compression. In reciprocating compression, you have a single acting compressor, double acting and diaphragm type compressor. In rotary compression, we'll be studying the lobe type, screw type, vane type, scroll type, liquid ring type. These are the different types of rotary compression. Okay. So basic difference in the reciprocating compression is that in reciprocating compression, the compression or we can say there will be a piston center device. There will be a delivery valve, suction valve. The air will enter from this side. When air will enter, what will happen? The piston will go to this side. The piston will be connected to a connecting rod and to a crank. When the air will be filled inside here, what will happen? Then during the compression stroke, the air will get compressed. Air will get compressed in the cylinder, and at high pressure, the high pressure gas will come out from the discharge valve. Okay. When the piston will move in this direction, the air will get compressed in this small volume. The volume will get reduced, the pressure will increase, and the high pressure gas will be released from here. This is a reciprocating engine or reciprocating compression. In rotary compression, what happens? In rotary compression, the gas will be compressed inside a small volume, but there will not be a reciprocating arrangement for that. There will be a rotary arrangement. There will be some rotating elements like gears. There will be some scroll casing. There will be some vanes. They will be rotating, and because of the rotation of them, the air will get compressed, and due to compression of that, the pressure will increase. Okay. Now, other is dynamic compression. Dynamic compression are based on the simple method of conversion of kinetic energy into pressure energy. In dynamic compression, the kinetic energy of the fluid will be changed into pressure energy. Basically, in dynamic compression, what happens? Firstly, we increase the kinetic energy of the fluid, and after that, we will be converting that kinetic energy into pressure energy. These are of two types: centrifugal compression and axial compression. Okay, in reciprocating compression, you have to remember one thing, that in reciprocating compression, if you have to ask you that what is the minimum work, will be given in the reciprocating compression, in which process? That is only possible in the isothermal process. If you do the compression in the compressor, it is only during isothermal compression in which you have to give the minimum work. So minimum work will be given in minimum work input will be in isothermal compression, and maximum work input will be in the adiabatic compression. Maximum work input will be given in adiabatic compression or isentropic compression. Okay, so basically in the case of a compression, because as you know that work input is given during the compression process, so during the isothermal compression, the minimum work input will be given, and during adiabatic compression, maximum work input will be given. Okay, the work input will be maximum. Clear everyone? Is it clear to all of you? Yes. So this is a very important point. Now, as you know that compression is an open device, in the case of a compression process, like in the case of generally either we will be doing adiabatic compression or isothermal compression is a very ideal case. Okay, generally either we'll be doing adiabatic compression or polytropic compression. In case of polytropic compression, the work input will be n by n minus 1, P2 V2 minus P1 V1. This is the formula for work of polytropic compression. Because in real application we do the polytropic compression. This is the formula for work input of polytropic compression. Now there are two cases in the case of compression. One is work input without clearance volume, and one other is work input with clearance volume. What is the meaning of clearance volume? As you know that these compressors are like a reciprocating cylinder. Okay, in the reciprocating engines or cylinder, we left some amount of space. We leave some amount of space, which compressor is used for low delivery pressure, low air delivery at high pressure. Okay, Akhilesh, the compressor which is used for low air delivery at high pressure, that is low air delivery at high pressure, that is reciprocating compressor, of course, because reciprocating compressor are meant for high pressure ratio. Okay, so my dear students, some amount of space is left inside the cylinder intentionally so that the piston should not strike on the walls of the cylinder and the cylinder head. That is called as clearance volume, right? In any reciprocating device, this clearance volume is generally left inside the cylinder. But in the ideal case, we don't leave any clearance volume in the reciprocating cylinder. But in actual case, we leave some clearance volume. In the ideal case, we'll be finding the work input without clearance volume. And the formula for work input without clearance volume will be this. This is the formula for work input per cycle. Work input per cycle in a reciprocating compressor without clearance volume. This is the formula. So always remember this formula. It is equal to n by n minus 1 P1 into V1 P2 by P1 over n minus 1 by n minus 1. This is the formula. One more important thing, that this formula can also be converted in terms of temperature. You can also write in terms of temperature. In terms of temperature, it will be equal to n by n minus 1 mRT1. As you know that P2 by P1 minus n minus 1 will be equal to T2 by T1 minus 1. So you can simply write it as n by n minus 1 mR of T2 minus T1. This is also the work input without clearance volume in terms of temperature. You can use this formula. Okay. Next is compressor work input with clearance volume. If we are using some clearance volume inside the cylinder, then what will happen? If we are using some clearance volume inside the cylinder, then the work input will be, because we are leaving some clearance volume, the clearance ratio is equal to ratio of the clearance volume divided by sept volume. We intentionally leave some amount of volume inside the cylinder, that is called as clearance volume, and the ratio of the clearance volume divided by sept volume is called clearance ratio. Generally we take 5%, up to 5% of clearance ratio is taken. Okay, so with clearance volume, the work input will be equal to this. This will be the work input with clearance volume. Only difference is that in the case of work input without clearance volume, we are using V1, total volume. But here we will be using V1 minus V4. This is the actual volume. So basically the actual volume will get reduced during the work input with clearance volume. The actual volume given inside the actual volume of air given to the compressor for compression will reduce. Okay, that is the difference between the work input with clearance volume and without clearance volume. Okay, now there is a term called volumetric efficiency. As you know that volumetric efficiency is equal to actual volume by effective volume. It is equal to 1 plus C minus C P2 by P1 power 1 by N. This is the formula for volumetric efficiency. It is a very important thing that to understand that if pressure ratio will increase, the volumetric efficiency will decrease. If pressure ratio will become equal, volumetric efficiency will become 100%. If clearance ratio will increase, volumetric efficiency decrease. If the coefficient of expansion will increase, volumetric efficiency will increase. Okay, so with respect to this formula, if the value of N increases, volumetric efficiency increases. If C increases, the volumetric efficiency decreases, and if P pressure ratio increases, the volumetric efficiency decreases. Now there is a term called as free air delivery. It is also very important term with respect to compression. What is the meaning of free air delivery? So basically, as you know that in the case of a compressor will be discharging some air at high pressure, right? And that high pressure air will be stored inside a receiver. So what is the meaning of free air delivery? Free air delivery basically is a reference point for comparing the volume handling capacity of different compressor. If you go to the market to purchase different types of compressor, there are two ways in which you can purchase the compressor. One is you can ask what is the power input that compressor will use for compression, and another thing is what is the amount of free air delivery. Free air delivery means what is the amount of air which will be delivered by the compressor with respect to inlet condition. Generally in the compressor, the inlet condition are the atmospheric condition, normal temperature and pressure. The inlet to the compressor takes place under normal temperature pressure. So if you want to see the delivery condition of the compressor with respect to suction condition, then that is called as free air delivery. So free air delivery basically means that if suction occurs under atmospheric condition, then actual sucked volume will be the free air delivery. Basically, it is the formula we use. This is the actual volume. This is actual volume is V1 minus V4 divided by temperature of the delivery, or this is T2 discharge temperature. This will be equal to the atmospheric temperature into volume. This is the free air delivery divided by the atmospheric temperature. Okay, so with the help of this formula you can find the value of the free air delivery. If you know the actual volume, if you know the value of actual pressure and actual temperature after compression, and if you know the atmospheric pressure is generally 1 bar, atmospheric temperature is 15 degrees Celsius. So by knowing this value you can find the free volume of free air delivery. So by getting the free air delivery you can understand that what is the capacity, volume handling capacity of the compressor. So that is a very important term. Now in the case of a compressor, reciprocating compressor, as you know that generally high pressure ratio are obtained by a reciprocating compressor and very less discharge you obtain in a reciprocating compressor. So reciprocating compressor are used for very high pressure ratio and low discharge. But there is a problem with reciprocating compressor. Then that problem is if you do entire compression in a single stage. If you do the entire compression in a single stage, what will happen? The pressure ratio will increase. Very high pressure ratio. And because of that, the volumetric efficiency will reduce. Volumetric efficiency will reduce, also the work input will increase. That is a disadvantage of a single stage compression. If you do single stage compression in reciprocating compressor, the work input will increase, the pressure ratio will increase, and because of that volumetric efficiency will decrease. Also what will happen? Yes, actual pressure is equal to delivery pressure, exactly, Shri Krishna. Okay, now that is why to avoid this disadvantage we'll be using multi-stage compression. So instead of using the achieving the pressure ratio that you want to achieve and achieving that in a single stage, we can do multi-stage compression. In multi-stage compression, you do one stage of compression. After that, we send the gas into an intercooler for heat rejection. Again, we will do the second stage of compression. Again, we will be using a second intercooler, and then we will use the third stage. For example, here we are using 3 stages of compression. We are doing the same compression thing in 3 stages. Okay, this is the first stage. This is the second stage and this is the third stage. Same thing we are doing in 3 stages. What we are doing in single stage. So what is the advantage of the 3-stage compression or 2-stage compression or multi-stage compression? The work input will reduce. Also one important of the multi-stage compression is that work input will reduce and the volumetric efficiency will increase. So these are the advantage of a multi-stage compression. Now in the multi-stage compression, we are having an important point called work input with perfect intercooling. There is a term called perfect intercooling. What is the meaning of perfect intercooling? As you know that in intercooling, we reduce the work input. With intercooling, the work input will reduce. So in the case of in which process the work input is minimum, that is isothermal. It is isothermal compression in which work input is minimum. So what is the meaning of perfect intercooling? Perfect intercooling is that intercooling in which the compression becomes isothermal compression. That means if this is the first stage of compression, then in perfect intercooling, T2 will become T1. This will happen in the case of perfect intercooling. Also in the case of perfect intercooling, the pressure ratio in each stage will become equal. That is P2 by P1 will become P3 by P2 and P3 by P2 will become P4 by P3 and so on. Okay, so with perfect intercooling, the compression will become isothermal compression and the pressure ratio in each stage will become equal. That is the advantage of perfect intercooling. So in the case of perfect intercooling, we have a derivation, and that derivation is in case of perfect intercooling, we have a derivation that is, I have to tell you. So what is that derivation? In perfect intercooling, as I told you, in perfect intercooling, the pressure ratio, the intermediate pressure will become square root geometric mean of the initial pressure and the delivery pressure. Intermediate pressure after, let us say it is a two-stage compression. For two-stage compression, the intermediate pressure for perfect intercooling will become the geometric mean of the initial pressure and the final delivery pressure. Okay, this will happen in perfect intercooling. Now this is just a case of two-stage compression. What will happen if it is a three-stage compression? Then how you can find the intermediate pressure? So there is a direct formula for that. Px plus 1 divided by P1 is equal to P2 by P1 over X. This is a direct formula for finding the intermediate pressure in perfect intercooling. It is a direct formula for finding the intermediate pressure in perfect intercooling in any stage of compression. Whether it is 2 stage, 3 stage, 4 stage, 5 stage, any stage of compression. Let's say if it is a 3 stage compression. In that situation, X will become 3. So this will become P3 plus 1 divided by P1 is equal to P2 by P1 over 3. So if it is a 3-stage compression, you will get this value as P4 by P1 is equal to P2 by P1 Q. So you will be, in the exam they will be giving you the inlet pressure. Inlet pressure will be given to you. Whenever they will ask you to find the intermediate pressure, they will give you inlet pressure. They will give you the final delivery pressure. Final delivery pressure will be given. Final delivery pressure in that stage. In the given stage. In any stage, for example, if it is a 2-stage compression, they will give you P3 and P1. If it is a 3-stage compression, they will give you P4 and P1. So that will be given. They can ask you to find the value of P2. So this is how you will be using the direct formula for finding the intermediate pressure for any stage of compression, whether it is 2-stage, 3-stage or 4-stage or 5-stage, any stage of compression. Okay? So that is the direct formula. Clear everyone? Is it clear to everyone? Please tell me, my dear students. Now there is also a direct formula for finding the minimum work input in perfect intercooling. And that direct formula is the direct formula for minimum work input in perfect intercooling for any stage of compression. And that direct formula is X into N over N minus 1 P1 into V1, Px plus 1 divided by P1, n minus 1 by Xn minus 1. So this is a direct formula. It is buffering. I think it is not buffering right now. Right now I can say it is not buffering, but let me check. Is it buffering now? Is it buffering? Is it still buffering? So this buffering has totally spoiled everyone's mood. I think I'm really sorry about that. Although buffering is not in my control because internet issues generally don't happen. As you can see in my previous session, the session were very smooth. But today it is. I don't know why it is happening today. Today it is causing a lot of problem. This buffering issue. So I'm really sorry about that. So this is a direct formula for finding the minimum work input of compression for multi-stage compression. Clear everyone? In this, X is the number of stage of compression. Px plus 1 is the final delivery pressure. If you know the final delivery pressure, P1 is the inlet pressure or suction pressure. So if they have given the value of inlet pressure, suction pressure, final delivery pressure and number of stage of compression, you can directly find the minimum work input in perfect intercooling. This is a direct formula. Clear everyone? Is it clear to everyone? Please tell me. Direct formula for finding the minimum work input for perfect intercooling. Clear everyone? So let's move on to the very important thing, degree of reaction. This degree of reaction term you will be studying in both turbines as well as in compressor. In the case of axial compressor or in the case of, especially in axial compressor, we use the stator and rotor. A stator is a stationary member and rotor is a rotating member in the axial flow compressor. Actually, axial flow compressor are used in the gas turbine power plant. They are also used in the aircraft application and many other applications. Okay, in the jet engine also we use axial flow compressor and also centrifugal compressor. But degree of reaction basically is a formula which tells you degree of reaction is equal to change in enthalpy or change in the pressure drop in the moving blade divided by change in enthalpy in the moving blade plus fixed plate. It is also equal to change in pressure or pressure drop in the moving blade divided by pressure drop in the moving blade plus pressure drop in fixed plate. This is a formula for degree of reaction. Okay, clear everyone? Now we are going to understand the steam turbines. Steam turbines is given in the syllabus of GATE 2021. So steam turbine is basically that component of a steam power plant which is used for converting the steam having some pressure energy into the mechanical energy. But do you know that steam turbine does not convert the pressure energy into mechanical? The steam turbine converts the kinetic energy which is given by the nozzle to the turbines. That kinetic energy is given by the nozzle. So basically what happens in case of steam turbine, just before the turbine we are having a nozzle. That nozzle, the steam from the boiler will not enter into the turbine. It will first go into the nozzle and after going to the, so basically from the boiler, the superheated steam will go into the nozzle. It will go into the nozzle, and from the nozzle the high kinetic energy steam will be given to the turbine. So basically this nozzle is also very important, but nozzle is not in your syllabus. Otherwise I would have told you about the nozzle also. So basically the superheated steam first will enter into the nozzle where the pressure energy will get converted into kinetic energy in the nozzle, and that kinetic energy steam will be given to the turbines. The blades of turbine will move by the kinetic energy of the steam, and that blades will produce some mechanical power at the shaft of the turbine, and that mechanical power will be given to the generator. So basically, if you have to study the classification of the turbine, so steam turbine can be classified into two types basis of principle of operation. On the basis of principle of operation, steam turbine can be classified into impulse turbine and impulse reaction turbine. So what are the impulse turbine? Impulse turbine are those turbine which works on the principle of impulse momentum principle. What is the meaning of impulse momentum principle? As you know that by Newton's second law of motion, the force is equal to rate of change of momentum, linear momentum. If you multiply this force with a small interval of time, dt, this will be equal to rate of change of momentum, linear momentum. This force into the product of very small interval of time, that is called as impulse. So when kinetic energy of the steam from the nozzle will be imparted to the blades of turbine, it will receive an impulse or it will receive a kinetic energy. Okay, so in impulse, the inlet energy to blades of turbine, blade of turbine is kinetic energy, is only kinetic energy. If it receives a kinetic energy, and because of that kinetic energy, some momentum change take place in the blades of turbine, and because of that change in momentum, the blades of turbine will move. Okay, so that happens in the impulse turbine. Now these impulse turbine are of it can be simple impulse turbine. Okay, simple impulse turbine is also called as D-level turbine. Okay, but the main problem of a simple impulse turbine is that in the simple impulse turbine, all the pressure energy is converted into the kinetic energy in the nozzle. All the pressure energy are converted into kinetic energy in the simple impulse turbine, and because of that, it gives you a very high kinetic energy. A very high kinetic energy will be received by the blades of turbine, and those blades of turbine will rotate at a very high rotation speed of 30,000 rpm. This much amount of high speed will be given to the blades of turbine, but blades of turbine are not meant to rotate at this much speed. Blades of turbine are meant to rotate at 3000 rpm speed. So that is why in simple impulse turbine we have to do compounding. Why compounding is done? Compounding is done in the simple impulse turbine in order to reduce the rotational speed of the blades of turbine and to reduce the loss of kinetic energy. So we'll be using these two types of compounding, generally velocity compounding and pressure compounding. Velocity compounding is called as Curtis turbine, and pressure compounded steam turbine is called as Reheating turbine. So these are the basically two types of turbine, velocity compounded and pressure compounded turbines, simple impulse turbine. Next is impulse reaction turbine. In impulse reaction turbine, what happens? Not only the turbine blade will have an impulse or kinetic energy, they will also be having some reaction force from the blades of turbine. That reaction force will come from the blades of turbine. So basically what happens in the case of an impulse reaction turbine? It will be having some fixed blade and moving blade. In the case of a simple impulse turbine, it consists of a nozzle and moving blades. In simple impulse turbine, all the kinetic energy is produced by the nozzle at the start only. In the moving blade, pressure remains constant. But in the case of impulse reaction turbine, pressure drop will take place both in the moving blade and fixed blade, and the velocity will increase in the fixed blade. Fixed blade will act as a nozzle in the case of an impulse reaction turbine. While in the moving blade also, because of the pressure drop, some amount of kinetic energy will increase, and that kinetic energy will cause the reaction force on the blades of turbine. And because a reaction force is received by the blades of turbine, in the impulse reaction turbine, that is, it is called impulse and reaction turbine. Now, impulse reaction turbine is of two types: 50% reaction turbine, which is called Parson turbine, and 100% reaction turbine, which is called Hero's turbine. What is the meaning of this reaction? I told you the term degree of reaction, right? Degree of reaction term I have told you. If degree of reaction is 50%, it is called 50% reaction turbine. If degree of reaction is 100%, it is called 100% reaction turbine. If degree of reaction is zero, it is impulse turbine. If degree of reaction is zero, it is impulse turbine. So for any impulse turbine, degree of reaction will be 0. Why? Because impulse turbine will not have any kind of reaction. Reaction will be only for a reaction turbine. Why impulse turbine will be having any reaction? They will not be having any reactions. So degree of reaction will be 0 for a impulse turbine. But for a 50% partial turbine, the degree of reaction is 50% for a impulse reaction turbine. So basically what happens in a simple impulse turbine, this is simple impulse turbine. In simple impulse turbine, we'll be having a nozzle and we'll be having a moving plate. In reaction turbine, we'll be having a fixed plate and moving plate. Okay. Power plant is different from fluid machinery. No, in the fluid machinery also the classification is same. But yes, in the case of the power plant, we use steam turbines because in the power plant, steam power plant, we have to turbine rotates with the speed of the steam. In the case of hydraulic turbines, it is the kinetic energy of the water which is given to the hydraulic turbines. So yes, that is a small difference. Rest, the classification of the impulse steam turbine and hydraulic turbines is almost same. Hydraulic turbine is also classified into impulse turbine and impulse reaction turbine. The impulse turbine in the hydraulic machinery is called Pelton wheel turbine, and the impulse turbine in the case of here is called D-level turbine, right? So in the simple impulse turbine will be having a nozzle. So in nozzle, what will happen? The pressure energy, the entire pressure energy will convert into the kinetic energy. So pressure will reduce. The pressure will entirely reduce in the nozzle, in the case of nozzle, and the velocity will increase in the nozzle. It will cause an increase of velocity in the nozzle. What will happen in the moving blade? In the moving blade, the pressure will remain constant in the simple impulse turbine, while velocity will decrease. Why velocity will decrease? Because that velocity will decrease because kinetic energy will be taken by the moving blade for their rotation. That is why the velocity will decrease. In the case of a reaction turbine, although we will be having fixed blade and moving blade, and they will be having a very special shape. They will be having a shape like that, which will be having a converging shape at the end, like this. This is how the blade of design of the blades will be in the reaction turbine. Okay. So in the case of a reaction turbine, the fixed blade will act as a nozzle, and moving blade, what will happen in the moving blade? In the moving blade of a simple impulse turbine, pressure will be constant. But in the case of a moving blade of a impulse reaction turbine, the pressure will decrease. The pressure will continuously decrease in the fixed blade as well as in moving blade. And the velocity will increase in the fixed blade and will decrease in the moving blade. So always remember that in the moving blade, velocity will always decrease because the kinetic energy is required by the moving blade to rotate. That is why velocity will decrease in the reaction turbine. Now there are basically three types of compounding. There are three types of compounding of impulse turbine. Compounding of impulse turbine. Simple impulse turbine is required. Why it is required? Why is it required compounding of impulse turbine? Because we have two problems. One is the rotational speed. The rotational speed is way too high. Rotation speed is very high, around 30,000 rpm. And at this 30,000 rpm, you cannot rotate a turbine in simple impulse turbine. Also, there is a loss of kinetic energy. There is loss of kinetic energy in the simple impulse turbine. So in order to cover that, we'll be using the compounding. Compounding basically means the connecting the turbines, connecting the nozzle and moving blades in a series in order to reduce the velocity, in order to reduce the pressure. So compounding is of basically three types, although it is pressure compounding, velocity compounding, and pressure and velocity compounding. But this pressure and velocity compounding we don't use. We don't use this pressure and velocity compounding. We use pressure and velocity compounding only. Pressure compounding is used in the Reheating turbine, and velocity compounding is used in the Curtis turbine. If you ask me which is more efficient, pressure compounding is more efficient. This is more efficient. Why it is more efficient, I will tell you later on. Pressure compounding impulse turbine. In the pressure compounding impulse turbine, we will be using the combination of nozzle moving blade, nozzle, moving blade, nozzle, moving blade. This combination will be there in the pressure compounding bus turbine. And with the help of this combination, what will happen? In the nozzle, what will happen? The pressure will decrease. And in the moving blade, what will happen? Pressure will be constant. And just after the moving blade, we'll be having another nozzle. Again, the pressure will reduce. Again, we'll be having a moving blade, the pressure will constant. Again, we'll be having a nozzle, again pressure will reduce. And again, the pressure will be constant in the moving blade. And in the case of if we talk about velocity, velocity will always increase in the nozzle. Moving blade velocity will decrease. Again, velocity will increase in the nozzle, it will decrease in the moving blade. Again, it will increase in the nozzle, moving blade decrease. So, in the pressure compounding, what we do, we will be having alternate row of nozzle and moving blade, nozzle, moving blade, nozzle, moving blade. And because of that, my dear students, please do not place focus on this side of diagram, it is not correct. Okay, please focus on this side diagram, it is not correct. Okay, it has to be moving blade actually, it is correct. Okay. So if you see this diagram, we'll be having nozzle, moving blade, nozzle, moving blades. And so because of this combination, both pressure is getting reduced in stages. Pressure is getting reduced in stages, so that at the exit of the turbine, we'll be having a pressure equal to condenser pressure. And velocity is also increasing. Velocity is increasing in stages. So that is why the pressure compounding is more efficient. It is more efficient type of compounding. Next is the velocity compounding. In the velocity compounding, we'll be using a combination of, nozzle, then we'll be using moving blade, then we'll be using the guide blade or fixed blade. Here the fixed blade act as a guide blade. They will not be causing any decrease of pressure or something like that. The only purpose of fixed blade. So in the velocity compounding, we'll be using combination of nozzle, then moving blade, then fixed blade or guide blade. Again a moving blade. This combination will be used in the velocity compounding turbine, simple impulse turbine. So in the velocity compounding, what will happen? As you know, we are having only one nozzle. So pressure will decrease only in the nozzle. And after that, the pressure will be constant. And what will happen is velocity compounding is basically used to reduce the velocity in stages. Velocity compounding is only used to reduce the velocity in stages, while pressure compounding is used to reduce both velocity and pressure in stages. That is the difference between velocity and pressure compounding. So what will happen in the moving blade? The nozzle velocity will increase, moving blade velocity will decrease. Again, the guide blade is not going to affect anything, either pressure or velocity. Only purpose of the fixed blade or guide blade in velocity compounding turbine is to direct the steam to the next row of the moving blade, to direct or transfer the steam to the next row of moving blade. That is the only purpose of the guide blade or fixed blade in the velocity compounding turbine. So neither pressure will reduce or increase, or neither velocity will reduce. In the moving blade, velocity will reduce, in the guide blade will be constant. This is what happens in the velocity compounding. So velocity compounding is basically done to reduce the velocity in the stages, while pressure compounding is done to reduce the pressure and velocity in the stages. Next is the reaction turbine. In the reaction turbine, we will be using fixed blade, moving blade, fixed blade, moving blade. And the good thing about the reaction turbine is that in the reaction turbine, partly pressure is reduced in fixed blade and partly in moving blade. That is a difference between the impulse turbine and reaction turbine. In the impulse turbine, complete pressure was getting reduced in the nozzle, and in the moving blade the pressure was constant. But in the case of a reaction turbine, pressure will be reduced in both both fixed blade and moving blade. Here fixed blade will act as nozzle in the case of impulse reaction turbine. Okay, Now we have to quickly wind up because a lot of time I have taken, and I have one more lecture at 10 p.m. So I cannot extend much because, as you know, that continuously I cannot take the session. So I have to quickly, because we have to solve some question also. So this is the difference between impulse and reaction turbine. In the impulse turbine, the pressure drop takes place only in the nozzle, and there is no drop of pressure in the moving blade. In reaction turbine, the pressure drop takes place both in fixed blade as well as moving blade. In impulse turbine, the cross section between the blade passes is constant, while here the cross section is converging type for fixed and moving blade. That is all difference. One more thing, that impulse turbine is used for small power and high speed. For small power and high speed, we'll be using this impulse turbine, and for large power and low speed, we'll be using the impulse reaction turbine. Now there are some design parameters of steam turbine. In steam turbine, there are some design parameters that I have to quickly tell you because we don't have much time. For impulse turbine, there's a term called as velocity ratio or optimum blade speed ratio. That optimum blade speed ratio is, let us denote by rho. It is equal to U by V 1. It is equal to cos alpha by 2. This is a formula for optimum blade speed ratio for impulse turbine, simple impulse turbine, where alpha is called as nozzle angle and U is the velocity of the blade, and V1 is the velocity of the jet at inlet. This is a formula for optimum blade speed. And for simple impulse turbine, the maximum diagram efficiency or maximum, this is the formula for maximum blade efficiency. Maximum blade efficiency of a simple impulse turbine is equal to cos square alpha. This is a formula for maximum blade efficiency of a simple impulse turbine. For an impulse reaction turbine, we only turbine which is important is partial turbine. Partial turbine is also called 50% reaction turbine or 50% reaction turbine. Why it has got 50% degree of reaction? Degree of reaction is equal to 50%. Why? Because in the case of partial turbine, it has got symmetrical. It has got symmetrical moving and fixed plate. It has got symmetrical moving and fixed plate. That is why it is called 50% reaction turbine. Okay, that is the reason it is called 50% reaction turbine, because of having symmetrical moving and fixed plate. Clear, everyone? So in the impulse reaction turbine, what we'll be studying here is that the degree of reaction will be 50% because enthalpy drop in the moving blade will be equal to enthalpy drop in the fixed plate. And because of that, it will be having degree of reaction 50%. For a partial turbine, the optimum blade speed ratio is equal to cos alpha, or cos alpha 1, where alpha 1 is the nozzle angle at the inlet. Sir, if this is tomorrow will be also class? No, tomorrow will be not a class of power plant part 2. Nozzle angle at inlet. But what I am thinking is we can solve some question of power plant today, and like 5 to 6 question, and remaining question we can solve in some other session I will take, because today I have one more session at 10 p.m. On the same channel in the late night series or qualified series. So I also need some time for dinner, and as you know that my session is continuing from it is already going from last such a great love I have you all have given today, some of the students. 5 dislikes, 75 likes. That means the ratio is perfect. I don't understand what is the meaning of dislike. So this is the optimum blade speed ratio, and the maximum blade efficiency is equal to 2 cos square alpha divided by 1 plus cos square alpha. This is the formula for maximum blade efficiency of our 50% reactor turbine. Now let us solve some questions quickly. In a gas turbine cycle due to intercooling, mean temperature of heat addition decrease, mean temperature of heat addition increase. Compressor exit air temperature will increase or none of the above. So what will happen due to intercooling in the gas turbine? When we do intercooling in the gas turbine, what will happen to the mean temperature of heat addition and all? Hi Mahesh Shinde, very good evening. Welcome to the session. Tell me the answer for this question quickly. So we'll be solving few questions today. Let us say 5 to 6 questions because I have taken around 15 to 20 questions, but we won't be able to solve today because as you know that I have one more session at 10 p.m. So hurry up, tell me the answer for this question, everyone. Arun is saying B. Fahad is saying option D for this question. Okay. Yes. So as you know that in intercooling, the efficiency will decrease. Intercooling efficiency will decrease. So my dear students, as you know that because in intercooling the efficiency decreases. So that means it is only possible if the efficiency is equal to minimum temperature of heat reaction divided by mean temperature. It is only possible that efficiency is decreasing if mean temperature is reducing. Okay, if mean temperature will reduce, then only efficiency will increase. So because we can say that in gas turbine due to intercooling, the mean temperature of heat addition will decrease. Mean temperature of heat addition will decrease with intercooling. Clear everyone? And mean temperature of compressor exit air temperature will increase. Compressor exit air temperature. Obviously, the compressor exit air temperature will definitely it will not be increasing, it will be decreasing actually. Okay, so the correct answer is option A actually in this situation. Next question, for a steam turbine working on a Rankine cycle, enthalpy at the inlet turbine is given, enthalpy at inlet to condenser is given, enthalpy of saturated liquid leaving the condenser is also given, pump work is also given. You have to find thermal efficiency. Yes, come on everyone, tell me the answer for this question. For a steam turbine working on Rankine cycle, the enthalpy at the inlet turbine is equal to 2800 kJ per kg. Enthalpy at inlet to the condenser is equal to 2061. Yes, tell me the answer for this question quickly. Hurry up, come on, tell me the answer quickly. What will be the answer? So they have given all the enthalpy at all the particular points. You have to draw the, if it is possible, you can draw the formula cycle also on temperature entropy diagram. So if you draw the cycle on temperature entropy diagram, it will be like this, temperature entropy. So basically this is, they have given the enthalpy at the inlet to turbine, this is 2800. Enthalpy at inlet to condenser is equal to, this enthalpy is 2061. The enthalpy at the saturated liquid leaving the condenser, this is 251.5. Pump work is equal to, pump work is 2.5. How can you find efficiency? Efficiency is equal to turbine work minus pump work divided by heat supplied. Okay? Yes. TNV Kishore has given B, Deepak has given D for this question as the answer. Yes, hurry up, be quick. Yes, Akash Gautam has given C. Okay. So different answers, students are different answers. I am getting different types of answers. I am getting here. So the right answer will be option B for this question. How can you find the answer? In this particular question, as you can see that, my dear students, the turbine work is can be easily find as H1 minus H2. It is equal to 2800 minus 2061. We'll be getting a turbine work. The pump work it is already given 2.5. What you require in this question is the heat supplied. Let us say this is 0.1, this is 0.4. So heat supplied will be equal to H1 minus H4. How will get the value of H4? Because pump work is equal to H4 minus H3, right? Pump work is given here. Even H3 is given here, this point. So you can say H4 will be equal to 2.5 plus 251.5. So from here you will get the value of H4. If you put the value of H4 here, you will be getting the heat supplied. Okay. So if you can find the turbine work, the pump work is already given. Heat supply also you can find from here. You will be getting the efficiency 28.9%. Good. Next question, in an air standard cycle with regenerator, air enters a single stage compressor at 100 kilopascal 20 degrees Celsius and leaves the compressor at 1 megapascal. The maximum temperature in the cycle is 1200 degrees Celsius. The regenerator effectiveness is 0.8. For air, gamma is given, Cp is also given. You have to find the efficiency of the cycle. Yes, come on everyone, how can you find the efficiency of the cycle? Yes, we are having a regenerative cycle. So try to be very much careful for solving the question. So how can we solve this question? Let us say that we have to find the efficiency in this particular question. Let us say this is 1, this is 2, this is 3, this is 4. Let us say this is 5, this is 6. Effectiveness they have given as 0.8. What is effectiveness? It is equal to T5 minus T2 divided by T4 minus T2. They have given this value as 0.8. In this question, they have given the value of temperature at the inlet. T1 is equal to 20 degrees Celsius, which is 293 Kelvin. They have given the value of T3, which is 1200 degrees Celsius, which is 1473 Kelvin. Right? So they have given the minimum and maximum temperature. How can you find the efficiency? Efficiency is equal to turbine work minus compressor work divided by heat supplied. Turbine work is equal to what? This will be H3 minus H4. Compressor work will be H2 minus H1. But what will be heat supplied here? Heat supplied will be H3 minus H5. This will be the heat supplied here in this case. Okay, my dear. So you can also write this in terms of formula, in terms of temperature. This is Cp of T3 minus T4 minus T2 minus T1 over Cp of T3 minus T5. This will also get cancelled out. Okay, so ultimately this is the formula. You have to find the value of T5. How can you find T5? If you know the value of T4, if you know the value of T2, you can find T5 from this equation. So tell me what will be the answer for this question, everyone. Hurry up. Hurry up, come on, be quick. Hurry up, come on, be quick, my dear students. You can find the value of T2. T2 by T1 is equal to pressure ratio over gamma minus 1 by gamma. In this question, they have given the pressure at the inlet is 100 kilopascal and pressure after compression at 1 megapascal. That is 1000 kilopascal. So pressure ratio will be equal to 10. Right? So T2 by T1 will be equal to 10 over 1.4 minus 1 divided by 1.4. So T2 you can get from here. You will be getting the value of T2, which will be 565.69. And if you know the value of T2, you know that T2 by T1 is equal to T3 by T4. T2 is known to you, T3 is known to you, T1 is known to you, you can find T4. T4 will be getting from here. T4 you will be getting from here, that will come out to be 762.963. Right, this will be the value of T4. Now because you have found the value of T2 and T4, you only require T5. T5 you can get from this formula, effectiveness. So if you put here, you will be getting T5 is equal to how much? T5 will be getting from here 723.486. 723.486 if you put the values. So what is the formula for efficiency? You are getting the answer. TNV is getting 58.3. 58.3, yes, that is the right answer. Very good. Option D is the right answer. You have got the value of all the temperature, T2, T3, T4, everything. Just put all the temperature here in this relation. You will be getting the efficiency 58.3%. Have you all understood this question? Tell me everyone. Have you all understood this question? Yes. It is a very good question. This type of question can be asked in 2 marks in the GATE exam. Okay? Yes, it will be D. The answer will be D for this question. Next question. Next question. Air enters in a compressor of Brayton cycle at 100 kilopascal and 25 degrees Celsius and compressed to 500 kilopascal. If 825 kilojoule per kg of energy is added to combustor, then back work ratio of the cycle will be. You have to find the back work ratio in this question. Yes, come on, tell me, everyone, quickly. How can you find the back work ratio? Yes, come on, everyone. Back work ratio. If you have to find the value of back work ratio, it is very simple because you know that back work ratio is equal to the compressor work divided by turbine work. Compressor work is equal to Cp of T2 minus T1 and turbine work is equal to Cp of T3 minus T4. You can also write it as T2. You can take T1 common, T2 by T1 minus 1, and you can take T4 common. This will be T3 by T4 minus 1. This will get cancelled out as they both are equal. So back work ratio is simply equal to T1 by T4. In this particular question, they have given the value of T1 25 degrees Celsius. T1 is 25 degree Celsius. If you somehow get the value of T4, you can get the answer very easily. So how can you get T4? They have given the heat added. Heat added is at constant pressure in the Brayton cycle. In the Brayton cycle, heat addition takes place between 3 to 2. So this will be equal to Cp of T3 minus T2. This is given as 825. Cp is equal to 1.005. 1.005 into T3 minus T2 is equal to 825. If you know the value of T2, you can easily find this T3. So how can you find the value of T2? You know that T2 by T1 is equal to pressure ratio over gamma minus 1 by gamma. Pressure ratio will be equal to what? This is 500, this is 100. So pressure ratio will be equal to 5. Just put the value, will be getting T2. T2 will be getting from here. What is the value of T2? Yes, the answer will be option A. Very good. 0.365. Good. Deepak and TNV Kishore. So T2 will be getting from here 472 Kelvin. 472 Kelvin will be the value of T2 from here. And if you get the value of T2, you know that T2, if you put the value of T2 here, so you will be getting the value of T3 from here. Okay, that is 1.005 of T3 minus T2 will be equal to 825. So T3 will be getting from here, right? So you will be getting T3 will be 1293 Kelvin. After getting T3, you have to find T4. So you know that T3 by T4 is equal to pressure ratio of gamma minus 1 by gamma. Or you can simply say that T3 by T4 is equal to T2 by T1. So you know T2, you know T1, you know T3, you can find T4 from here. T4 will be equal to how much? 816.4. Just put the value everything. You have got T1. T1 is 298. T4 is 816.4. You will be getting the answer as 0.365. Are you getting the answer, everyone? Yes. Next question, question number 4. In an ideal Brayton cycle, so we'll be taking 2 more questions because I have taken 15 questions, more than 15 questions for this session because we are not having much time. So what I'm going to do is, if you guys are promising me, that I have a late night series, okay, I will not do that because now I will not be having any session in this crash course. So how will be completing the rest of the questions? Well, we can do this thing, but that is not allowed actually. We can cover the rest of the question in the late night series at 10 p.m. But those students who don't know about this class, and they will come to the class as new, like in the late night series tomorrow today at 10 p.m. I will be teaching force on submerged bodies. So those students who will not be knowing about this session, because if I promise that I will take rest of the question in that late night series of power plant, so those students who will be new, they will be thinking why we are solving the question of power plant. No, tomorrow we will not be taking any class. Tomorrow is holiday. Okay, it is 1st of January, so there will be no class. Okay, I will put the question in PDF. Okay, so in an ideal Brayton cycle with regeneration, air is compressed from 80 to 400 and 175, heated to 450 in the regenerator, and is further released to this much. Treating air as an ideal gas, find effectiveness. So it is very simple question. It is very simple question. They have given all the temperature. They have given all the temperature. You just have to find effectiveness. This is 1, this is 2, this is 3, this is 4, this is 5. So they have given that temperature at the inlet is 10 degrees Celsius. This is 10 degrees Celsius. This temperature is 175. T5 temperature is equal to 450 degrees Celsius. And T3 temperature is 1000. So all the temperature have been given. How can you find effectiveness? For effectiveness, effectiveness will be equal to T5 minus T2 over T4 minus T2. You just need the value of T4. If you know T4, you can find effectiveness. So how can you find T4? They have given the value of P1 as 80 kilopascal and this is 400 kilopascal. So pressure ratio is equal to 5. Okay, so you can simply say that this T3 by T4 will be equal to pressure ratio over gamma minus 1 by gamma. So T3 is known to you 1000 degrees Celsius or 1273 Kelvin. So you will be getting T4 from here by this relation. Just put the value of T4 in this relation. T5 is already known to you. T5 is given 450. T2 is given 175. Everything is given. You can find effectiveness. Tell me the answer quickly. Come on. Tell me the answer quickly. Come on, be quick. T4 will be getting 803.75. 803.75. So just put the value. You'll be getting the answer as 723. 723 because 450 degrees Celsius 723 minus T2. T2 will be equal to 448 divided by 803.75 minus 448. You will be getting the answer as 77%. Are you getting 77% for this question? So that is a very good question that can be asked in the exam. Okay, from effectiveness. Let us solve the last question, question number 5. I will give rest of the question in assignment. Rest of the question I will give you in the assignment in the PDF, and if you are not able to solve the question, you can ask me in the Telegram group. Okay, I will give rest of the question in the Telegram group, and if you are not able to get the answer, then you can ask me the solution in the Telegram group. Okay. So because I have to end the session because I have one more session at 10 p.m. So definitely I need a break also. So that is why I cannot take continuous sessions. You have to find the pressure ratio for maximum work capacity. This type of question can come in 1 marks in the exam. Come on everyone, be quick. The optimum for maximum work capacity, the pressure ratio is the optimum pressure ratio, and that will be equal to maximum temperature divided by minimum temperature gamma over 2 times of gamma minus 1. This is a formula for optimum pressure ratio. So just put the value, maximum and minimum temperature are given. Just tell me the answer quickly. Come on, be quick. That will be 900 divided by 400 over 1.4 over 2, 1.4 minus 1. You'll be getting the optimum pressure ratio. How much? What is the answer for optimum pressure ratio? Yes, it will be 4.13. Okay, so that will be the answer. So with this, I would like to conclude the session because I have got many questions left. But okay, let us take this as the last question, question number 6. For a 4-stage reciprocating compressor, the suction and discharge pressure are 1 bar and 15 bar. The optimum pressure ratio per stage for minimum work input. Tell me the answer for this question. Very good, very good. The answer is correct. Very good. Let's take it as a last question. What is the meaning of optimum pressure ratio? Optimum pressure ratio means P2 by P1 it is asking. What is the value of P2 by P1 they are asking? You have to find the optimum pressure ratio for 4-stage. I told you that a direct formula Px plus 1 divided by P1 is equal to P2 by P1 over X. In this question, you have to find the optimum pressure ratio for minimum work. They have given the value of 16. This final delivery pressure, inlet pressure is 61. P2 by P1 over 4. So what will the answer? Tell me. The answer will be option B. Very good. Okay. So optimum pressure ratio per stage means this is P2 by P1 you have to find this question. Final delivery pressure is given 16. Discharge inlet pressure is 1. These two are given in this question. This you have to find. You will be getting this as P2 by P1 will be equal to 16 power 1 by 4, which is 2. Okay. So with this, I would like to conclude the session. Next question you can take it as homework. This is question number 7 in a gas turbine with intercooler and reheater. With intercooler and reheater, what will happen? With intercooler and reheater, mean temperature of heat supply will decrease and mean temperature of heat reaction will increase. So this will be the answer for this question, option D. This is a question you have to find the optimum pressure, optimum value of pressure to obtain maximum work. Here you have to find the optimum value of pressure. This will be compressor work efficiency to turbine efficiency into maximum temperature divided by minimum temperature over gamma of 2 gamma minus 1. This will be the formula for the optimum pressure ratio. So it is very simple. You know the efficiency of compressor, turbine, both are given. It will be 0.8 into 0.85 into maximum temperature is given 1073 by minimum temperature is 330 whole power 1.4 by 2 1.4 minus 1. This is how you will be finding the optimum pressure ratio. Clear? So this is the last question we are doing, question number 8. Now we will be ending the session. I will not take much question because I feel like I should give you the answer for all the question, but it is not possible because we are lagging in time. We have to complete the session quickly. Okay. So what will the answer for this question? Tell me, what will the answer? Everyone. If we solve it, we will get this 4.736. You can verify it also. So that is question number 8. Now next question you can solve it by yourself. Question number 9, 10, 11, 12, 13, 13, question number 13 is important. Question number 13. I will tell you the solution for this question. For a single stage impulse turbine with a rotor diameter of 3 meter and speed of 35 meter RPM, when the nozzle angle is 20 degree, the optimum velocity of the steam. Optimum velocity for an impulse turbine is equal to U by V1. That is cos alpha by 2. Alpha in this question is 20 degree. U you have to find as pi dn by 60, which is pi into d is 3 into n. This is 3500 divided by 60. You have to find the value of V1 in this question. Okay. So optimum velocity of the steam for a single stage impulse turbine will be given by this relation. So V1 will be equal to 2 into U by cos alpha. Alpha is 20 degree in this question. Okay. So what will be the answer for this question? Come on, tell me. If you solve it, you will be getting V1 as 1170.12 meter per second, and it is also equal to 4212.4 kilometer per hour. So both option B and C will be correct. Okay, so this is the last question of this session. Rest of the question I will give you as homework. You can solve this question. These are very simple question. Here you have to find heat rate and efficiency. You know the formula of heat rate and efficiency. You can simply solve it. This is also a very simple question. So this is question number 9. You can solve it as homework. And if you don't understand the solution, you can ask me. This is question number 10. It is also homework. You can solve it. This is question number 11. This is also homework. You have to find maximum network and optimum efficiency. So maximum network will be equal to what? Cp of root of T maximum minus root of T minimum whole square. And optimum efficiency will be equal to, for maximum work will be 1 minus root of T minimum by T maximum. You can use this formula for solving the question. In this question, heat rate will be equal to heat supplied by net work. Heat supplied divided by net work. If you are not able to solve it, you can tell me. And efficiency is equal to 1 by heat rate. This question I can tell you the answer. This is question number 12. Which of the following is true in case of gas turbine? The maximum efficiency corresponds to optimum pressure ratio? No. The maximum work output corresponds to optimum pressure ratio? Yes. The maximum efficiency corresponds to maximum pressure ratio? Yes. Okay. So for this question, question number 12, the answer will be option B and C. Clear? So only 2 questions are homework. Question number 11, question number 10 and question number 9. 3 questions are homework. You can solve this question. Okay. And I will give you this PDF of the session in the Telegram group. So before we end the session, I have to tell you about our Vision course. If anyone is interested for GATE and ESE 2022 preparation, you can join our Vision 2022 paid course. These are the expert faculties or star faculties of mechanical. This is a list of our achievers who have scored good rank in GATE and ESE exam. If Grade Up Super you have not still taken, you can also take our Grade Up Super. With Grade Up Super, you will get access to all our paid courses with single subscription of Grade Up Super, and also you'll be getting Grade Up Green Card. With Grade Up Super, you'll be getting our paid courses of 3 month, 12 month, 18 month and 24 month at these cost. Okay. So that is all for this session. I will upload the PDF in Telegram group. Grade Up ESE and GATE /ME preparation. So you can join our Telegram group of Grade Up. This is the official Telegram group. You can join this Telegram group. I will upload the PDF in the Telegram group of this session. You can solve the remaining question given there. Okay, clear everyone? So I will see you in some other session on the Grade Up YT channel. And from today onwards, our late night series is also starting. Today onwards, I will be taking the topics of fluid mechanics. And today at 10 p.m. I will be taking the topic of hydrostatic forces, or basically forces on submerged bodies. Okay, so thank you so much for this session. And if you have enjoyed the session, please also hit the like button. Please like the session and share the session also. So thank you so much and Happy New Year to everyone. If some of you will not come to the 10 p.m. session, then Happy New Year to everyone, those who have joined me. And I hope this session must have helped you in your preparation journey for GATE 2021. I will come back with some more session like that. Okay. So thank you so much for joining me for this session and have a very good day. Late night series will be at 10 p.m. Although it is at 11 p.m. but today it will be 10 p.m. because most of you must have to celebrate New Year at 11, after 11 maybe. So that is why the class has been shifted to 10 p.m. today. Okay. So late night series today will be at 10 p.m. and I will be taking the topic of force on submerged bodies. Clear? So I will see you today at 10 p.m. also in the late night series, in the qualified series for GATE 2021. So thank you so much for joining me and have a good day. Thank you. And Happy New Year also. Happy New Year to everyone.